you can also send me over Canvas, but I will tell you, if you really need as quick as possible, emails is better. Okay, because with emails, as many of you probably the same, you're checking emails all the time. I don't know, like the same as your text messages, like maybe every half an hour. And if it's urgent, I will try to reply as quick as possible if it's short answer. If it's long answer, I will need to find time near computer, and I'll try to respond in 24 hours. So I have my office hours on Monday from 2 to 3 p.m. It will be over Zoom, and could be by appointment. And here I want your output, guys. First of all, how many of you can make it from 2 to 3 p.m. as office hours? I want you to use this opportunity to use all the buttons in your participants. And I want you to press yes if 2 to 3 works for you. And press no if 2 to 3 doesn't work for you.
Where are we pressing? What? How do you do that? I don't know how to do that.
So I want yes and no's. So if there is nothing, it implies that you still figure it out. Could you figure it out, Arthur?
I was not able to figure it out. I don't, but
You should go, guys, how do you do it, guys? You need to look. Could somebody who did this before explain? Because I'm in a host environment, so for me it's hard to say. Probably you should go to participant, and then in the participant you can choose your respond. Manage. Okay. I'm still missing quite a few yeses or no's, yes or no. If there is a blank, it implies they didn't participate. I want yes or no. Will 2 to 3 works for you?
So for the people so if you haven't clicked the yes, so if, instead of typing it in the chat, when you click participants, there are a couple of icons. And so it's raise hand, yes, no. So I guess that's where you meant, right? Yeah.
You can see that right now there is a red and green buttons, and now I start to see no's. Okay. Now I can see statistic, guys. And that's will be a way for me to communicate over Zoom. And I'm not sure, maybe other teachers will use similar standard style. It's very nice. I will have it all the time. And if somebody send me go faster, go slower, you don't have to tell me I want to go for a break or something or went away. I will not see this, but if you want me to slow down or speed up, like if something is very easy, you can send me signs, or if I ask you a question like this one, you can say yes or no. And in this case, we'll have some statistic and I get your output, because some of you have put a video on, but many people don't feel comfortable to put a video, and this way I could have a response back. Okay. So 13 people, for 13 people it works, and for some people from 2 to 3 doesn't work, and some people still did not respond. Guys, I want from you respond. That's a way for me to know that you could use this method of corresponding. Please put yes or no for office hours. It's my way of testing that you know how to use these buttons. I'll just go over names, like in the class. Araceli, I see that you didn't respond back. Please choose yes or no. Will 2 to 3 works for you? The same for Theodore. Then I have the same thing for Mar. And that's it. I have 3 people who are missing yes or no's. Okay.
This is Omar. 2 to 3 wouldn't work for me. I have a class during then.
In this case, press no.
Oh, my bad.
Okay. I just want to make sure, guys, that you all know how to use these buttons. I know it's everything right now slowly. We'll take like half a class right now just to make sure that we get a style with you guys, and then we'll go over lecture. So everyone, great. I could see that everyone managed to find how to use the buttons. Great, awesome. I'm very happy with that. And so 16 people, for 16 people, 2 to 3 works. and only for 4 people it does not work, which is pretty good. Okay, guys, question for everyone who I want from everyone to clear all. I could press clear all for everyone. For these 4 people who said no for me, will time from 6:15 after this class for 15-20 minutes after class works for you? Just for these 4 people who did not cannot make it from 2 to 3. Perfect. It works for everyone and everyone else. So guys, my official hours from 2 to 3, and if you cannot do it after the class, we can stay and answer some questions. It's for everyone else as well. If you couldn't make it 2 to 3, I could stay here for, let's say, from 6:15 to 6:30, and if you need it a little bit longer, but I don't want to stay too much long, okay? But this is your opportunity to have additional office hours. Okay, I'm glad that we sorted out. Okay, so that's done. So office hours, guys, how do you want it from me? And I know that it will be hard to say yes or no, maybe some outputs. Will you prefer, you can use a chart in this case. Will you prefer to have office hours that I specifically use the same and always be on here? And if you probably this is the style which I use. I will have my Zoom meeting the same link which you're using for the class. I'll have class on. If I'll see people in this case, I'll turn on video and answer your questions. If you're not here in this case, I will just work on my computer and have this program in the background. The same as I would sit in my office and waiting you to come in. Will it work for you guys? Perfect. Yes, I see some responses. Great. So next point. Awesome. I'm glad people started like, yes, I see feedbacks. Great. Okay, now let's talk about book. So that's our book, guys, Thermodynamics and Thermal Physics book. And usually, guys, if you use my notes, you don't have to have this book, okay? And you can have it for your problems. Sorry, it's my first lecture. Just a second, let me close that door. So you can use this book, guys. It's a very good book. It's, in my opinion, it's one of the best books. These books I used myself when I was an undergraduate, like 10 years ago. And that's absolutely amazing. This is a book which used in most of the universities, in my opinion, compared to many other subjects. They've used different books, but thermal physics is the best one. So we'll use that one. I pretty much follow this book. We'll skip some of the sections, but I'll try to cover as much as possible of this book. We miss just here and there just a little bit. However, if you have a good notes for my class, you don't really have to have this book. It's good to have, but you don't have to. But you need this because I will give you some problems for homework. So as an option which I used before, so for some students who cannot afford to buy a book, I could make pictures and put the problems in Canvas, just scan from the pages. And in this case, you can have access to the homework. Please let me know, guys, who needs this homework, or everyone have this book, some kind of digital or physical. Please let me know if you need your homework as a scans and Canvas. Did you understand my question? So if you have this book, you're all set. You have my lectures plus this book. But if you don't have this book, in this case, I make a scans of homework problems for you. Does anyone need these homeworks? Wow, everyone absolutely happy and satisfied. Great. Oh, I see some response in chat. Okay. Oh, I see one person have a scans. Okay. Okay. Some people would like to have a scans, please. Okay. So I will have a scans of the homework problems. I couldn't scan for you a book because it's rights of the publisher, but I could scan you a couple pages of the problems itself. Okay. So I will do that. So if you don't have a book, I mean, I strongly recommend it, but you can survive this class without it. Okay, next point. About preparatory, you need to take classes Physics 301 and Physics 375. Because if you don't have these classes, prerequisite classes, you have to drop out this class. You cannot be in this class without these prerequisites. Okay, questions? No? Okay. So we will cover some topics on thermodynamics. We'll start from topics for the first week or two. We'll cover something which you heard before, but after that, we'll start to cover materials which I'm expecting you don't know before. We'll discuss about entropy. In my opinion, it's one of the most coolest thing in physics. And when you think about physics from entropy points, it's become much more sense. We'll discuss Boltzmann distributions and boson and fermions and how we can do calculations for them. And that's pretty much and you can see everything else in contest. Let's talk about homework and exams. They have a 12 homework. Oh, I'm sorry, guys. I realize I have a here mistake. I put 12 homework, but in reality, it's 10 homeworks. Okay. So you can see here in the schedule, we have a 10 homeworks. My bad. Originally, I was planning to make it 12, but then I decided to have 10. So you'll have a 10 homeworks, and I will assign you in each Wednesday on a class, and it will cover usually everything which covers up to this Wednesday, including this Wednesday, and it's due Wednesday by 5 p.m. Before this class started. You need to submit it on Canvas. Okay. And if you submit me homework later, you will have a penalty 25%, which make it fair because I'll plan to put on Wednesday in the evening solutions, and it's unfair for people to receive a full credit if they have access to solutions and if someone else did it without solutions. So make sure you submit it on time. Let me know if you have a trouble to submit it on Canvas. I hope by this time you learn how to do it. You can take a PDFs and you can take just with a phone pictures and you can upload it. Guys, do you know the program which there is also programs which you can just with a phone create a PDF, free programs? You can, if you have, sometimes if you don't have a scanner, you can just use a phone, and there is a program which could just take a pictures, and if it's documented, immediately will find the borders and create. You can scan many pictures, and it will create one PDF, and then you can submit as a PDF. Please let me know if you need name of this program, and I could send you the name of this program, or you can share in a chat if somebody needs it. Okay. CamScanner, exactly, yes. This is a program which I used before, exactly this one. You can just scan and it's very easy to use. Make sure you get familiar with that because everything is online. Questions? No. So at least I see some faces. It's nice I see some response back. Okay, so let's talk about grades. We have a final exam, which will be 20%. We'll have 2 midterms, 20%, and homework will be 40%. I'm not sure exactly how we'll do final and midterms. I'm trying to figure it out. We'll try to arrange it during the class time. So usually I try to cover in my live classes, you're allowed 1 or 2 pages of notes, and it's closed books, but you have 1 page of notes where you can write whatever you wanted, and you have a class time to do the problems. But we'll see how we'll do it online. I will right now still investigating what is the limitations for me to ask from you. Okay, but my goal is that we'll try to do it during the class. So if you have access to it, you still have it. And I most likely, I will ask you to be in Zoom. And that's why it will benefit you, because if you have a questions, you can immediately ask me and I could respond back the same as you will be in the class. And most likely if you have a question, someone else may have in the class a question. So we'll use this format, and then you will have time immediately after the exam to submit your work. And if you have some difficulties with connection, we'll try to figure it out, okay? So that's most likely the style which we'll use, but I still just need to double check if there is any specific limitations this style. Okay, I put here as extra points, 5% for class attendance and quizzes. It's above 100%. So I may do some quizzes and ask you some questions, and this is just additional bonus points. Okay, so it's always good to participate and attend. And usually people like my lectures. I'm not sure how it will be online. I hope you will enjoy. Grading is a standard. I'm sure you saw it so many times, so I don't see point to go over that. Okay, let's talk about last bit here. And so here's the schedule for each week. So here you can see it. It's almost here full of it. So you can see I tried to put for each of the week what kind of topics we cover. And here's in about we have a chapters which corresponds to the book. And you can see we pretty much follow the book. And here there is some holidays, and I put for you some midterms. And you can see there is a reviews before each midterm and before the final exam. And here's the days when I will give you homeworks. It's Wednesdays, and I'll show you when it's due. And here we have only one, I think, one exception here. It is homework 8. I ask you to submit it on November 12th, because November 11 is a holiday. Yeah, and I don't want to assign you for the day when it's a holiday, but I'll give you additional day. But I want you to have a possibility to submit me this homework, so I could put solutions. So before the midterm 2, you have access to all solutions, so you can prepare over weekend. Okay, so that's the reason behind it. But I think everything's straightforward. If I will be away from the schedule, it's maybe by half of the lecture, but it will pretty much follow this class. Okay, and as you can see, it's continuing. We will have a final exam here. Okay. Questions? I think this syllabus is quite straightforward. So if you have any questions, it's time for you to ask me. Okay. We have easily can talk about at least for 7 more minutes about the syllabus if you have a question, guys. Okay, everything's good. Okay. Okay. Oh, I have a question, guys. Could you read well this typing? Yeah.
Yes.
When I write. Okay, good. So, a few more things about homework comments. Here's a few cartoons for you. Please explain your steps. I don't want to have something like that where you give me like sort of initial formulas, then tell me that miracle occurs, and then you give me the final answers. You need to show me steps, how you get from A to B. Okay. And make sure you put the units. I'm sure you're in the 4th year, but I'm sometimes still find students who surprise me, who writes 6 digits after the dot when there is only 2 digits of accuracy of the questions, whatever it is. So make sure you use the proper significant figures. If you're not sure how many significant figures you need to put 3 significant figures, okay? It's sort of rule of thumb if you're not sure, but usually you can look how many significant figures in elements, and this is how you know. Just simple rule of thumb. Make sure you put units, because if you did not put units and you measure how much energy it's needed to warm up object, I assume your units are oranges, and you are not measure energy in oranges, and I assume that you did it wrongly. Okay. So if I see missing, I mean oranges, I'm like, why do you measure distance in oranges? That's wrong. So that's how I'll treat it. Okay. So make sure. Okay, another, my favorite contour cartoon. Always label your axis, okay, and units when you put graphs. Okay. I'm done. So make sure you do well your homework and explain your answers, and I will try to give you feedback, and you can see how I do my solutions, so you see the style. I just try to raise your bar, how you do things, and I'm sure you do all awesome. It's not your first physics class. Okay, so we'll start our first lecture now, if you don't have any more questions. No? Guys, and I will not see immediately. Let me try to put chat so I could see the chat. Sorry. Okay, I will see the chat. So if you have a question. Oh, I have a question here. Sorry, let me double check. If I miss anything else. So it was a question. Will you be recording the Zoom meetings? The answer is no. I did not plan it. Why do you want me to record the meetings? I prefer not to record it, but I assume that you'll take notes. What I can do, I'll prepare these notes, which I'll write it down. And the thing is, I don't want to immediately say that I will post them online for you could scan and post it, because in this case, you stop doing your own notes. How about that, guys? If you miss the class and you need the notes, you can contact me and I'll give it to you. Okay? And if you think that I will have too many people who needs it, I may start to put it online, but I don't want to record Zoom meetings. Okay. If you think that you cannot attend or you have a problem with difficulties to attend the class, or with hearing what's going on and you need to go back and forward, let me know and I might change my mind and I start to record it. Okay. So what we can do after this class, I will start this class and some people who have more questions, and we can discuss this. So I'm very open to suggestion. If you think I need to record it, I can do it. I prefer not to. It's extra work. And I remember when I tried to do recording before, I have several times when my recording fails and it doesn't want to save it well. So I have a couple fails with this. So I'm not looking forward for that. But if you need it, guys, I will try again. It's much easier to do pre-recording than when you record over Zoom. I don't know. I had trouble with my computer. But we'll discuss it if you want it, okay? Okay. So we'll start with our first big section. It will be energy in thermal physics. And okay, let me adjust. Sorry, I'll just adjust it out and prepare it for. So we'll have several subsections. And first subsection will be macroscopic and microscopic point of view. Macroscopic and microscopic point of view. Point of view. Okay. Okay. So after that, we'll have a first subsection. We'll talk about macroscopic point of view. Okay. So let's talk about macroscopic. So usually when we're discussing microscopic, we're discussing something in the bulk, and our attention is focused on the system and everything outside the system, which has a direct effect on its behavior, like surrounding areas. Like, for example, this laptop. This is a microscopic point of view. It's a big thing. And I'm looking what is the temperature outside of it, what is the air. This is a microscopic point of view, okay? So, and you'll see how it's different when we're talking about microscopic. So macroscopic, attention is focused on the system. Okay, and everything outside the system. Okay, which has a direct effect on its behavior. Okay, which has direct effect on its behavior. So we call it surroundings. Yeah. Okay. So attention is focused on the system and everything outside the system, which has a direct effect on its behavior, surroundings. Example of it is pressure, velocity, volume, temperature. This is all macroscopic variables. Material. Okay. This all are macroscopic description. Okay. Macroscopic description. Okay. Or I can talk about when you have a microscopic description or coordinates. Okay. So what's the difference for that particular case? We have no specific assumption about the structure of the matter. So we don't care where is each of the molecule locates, yeah? So we don't care how exactly it's structured. We're talking about as a whole thing. For example, you are as a microscopic system. I don't care where each of your hair lay down, okay? Or how exactly you're breathing at this point. Where is your molecule of air going inside of your body? I don't care about these things, okay? I don't care about other small structures, like small structures of inside of this thing. So I'm talking about the whole system overall. And what's important, also macroscopic coordinates can be measured directly in general. So I could find out, measure directly, for example, where are you locating? You're locating in this particular house, yeah. For me, it will be very hard to measure where your particular red blood cell locating, yeah. I couldn't tell you exactly where each of the red blood cells locates. This is microscopic, but I know I could specify where you locating. You are macroscopic point of view. So a few small subpoints. So we have no specific assumption about the structure of the matter, no specific assumption about the structure of the matter, about the structure of matter. Okay. And we have macroscopic coordinates, and they could be measured directly in most of the cases, yeah, in general. Okay, in general. Sorry, I cut this word here, in general. Okay. Okay, now let's talk about second case. Let's talk about microscopic point of view. Okay. Microscopic. Okay. So in this case, we assume that material consists of n particle or molecules which have same mass and moving independently. Okay. So, for example, when we are taking, and we'll talk about a gas, so that this container have a gas, we look that, oh, this gas has this particular molecules, we assume they're same, and each of them moves randomly in each direction independently. This is assumption for microscopic point of view. So we assume that material consists of n particles or molecules, okay, and also consists which have same mass and also they're moving independently. Okay. So each particle can be defined by its position and velocity. So each particle can be defined by its position x, y, z, and its velocity vx, vy, vz. Okay. So that's called phase space. Okay. Also, I want to specify that we can look on it. Oh, sorry, I'll let you time to write down. Guys, let me know if I'm going too fast, if you want me to slow down more often, okay? It's my first time try to mimic classes over Zoom. But I hope in this style you'll have a notes. So microscopic point of view, we assume the material consists of n particles, molecules which have same mass, moving independently. Each particle can be defined by its position and velocity, x, y, z, vx, vy, vz, which called the phase space. Okay. Or we can talk about subsmall spaces. So instead of talking each individual, we can talk about small subgroups of particles which have its own energies. Okay. Or we can talk about subsmall spaces. We can talk about subsmall spaces. Subsmall spaces with Ni particles and with Ei energy. Okay. So in this case, our total number of particles could be represented as subgroups N1 plus N2 plus blah, blah, blah. And we can talk about total energy as N1 times E1 plus N2 plus or times E2 and so on. So here we have total number of particles, and here we have a total energy. Okay. And this model used in statistical mechanics. And we'll use it later in the course. Okay. Okay. So when let's see, when we use a macroscopic point of view, so we need to have assumption or which we need to make concerning the structure of the matter existing of the molecules. At this point, we care how it's made of. In a macroscopic, we said we don't care how it's made of. Now we care. And also, when we go to microscopic point of view, many quantities must be specified. We need to specify location of each of the molecules, what is the directions, and so on. And sometimes these quantities are not obvious. Obviously, it's very hard to measure where each of the molecule goes. And obviously, we cannot measure these values. So it's become tricky. So let's look now part 3, here subsection number 3, microscopic versus microscopic. Microscopic versus microscopic. Okay. Guys, could I move this away? Okay, maybe I'll like shift it like that in case if somebody still needs it. So when you look at like them together, look like they're different in the incompatible. You cannot use one system where it's microscopic, just each of the atoms, and somehow use the parameters for macroscopic point of view, or back and forth. And it sounds like it's like we can just look at it in like under like sort of like under microscope and see where each of the molecule moves, or we just look at step back and we see all of it together. And it's very hard to see how you can relate one with another. And what we need to understand, guys, we're looking in the same object. So in the end, they should agree with each other. If you're looking under the microscope and try to understand the pattern, try to figure it out how the whole object behaves, or if you look in a big picture, they both should come to the different or to the same conclusions, yeah? So the only difference is that microscopic goes beyond our common understandings. So sometimes it becomes too specific and it's very hard to understand. It's much easier to understand that, oh, we heat up the pot and pot get hotter and the water get boiled. And temperature goes up. It's very easy for us to understand, but it's much harder. Obviously, in this course, we'll talk about how each molecule start to move quicker and faster, and we'll talk about degrees of freedom, for example, changing with the temperature. But it's much less into it's hard to use your intuition to do that. But there is some relationship. So you'll find out very soon that few direct microscopic measurements describe average over a period of time of a large number of microscopic characteristics. Okay, so few direct macroscopic measurements describe average over a period of time of a large number of microscopic characteristics. Okay. So guys, could you tell me a few examples of it? Let's talk about a few microscopic points of view. We talk about pressure, volume, temperature. Yeah. So how we can look from microscopic point of view? You can turn on the and speak out for right now, or whoever. Just it's a question for you as a class, guys. Could you give me example how, for example, we can describe temperature, its microscopic measurements, and what it will describe over a long period of time. Oh, sorry, that's over a period of time of a large number of microscopic characteristics. What kind of characteristics will describe temperature?
Average kinetic energy.
Yes, as the energy increase, yes, the particles move faster. Yeah. If we know they have a high energy, in this case, the whole object will start to have a high temperature. Very good. Temperature. Related to speed of particles, okay? Speed of particles. Okay. How about pressure? How we can describe what is the pressure on something? So how do we know what is the pressure on our hand? We know that there is a or for example, you put the object and you can say that, oh, it's pressure, it's pressing on something else. But pressure is macroscopic. How we can describe it from microscopic? Someone else?
Force per unit area.
Okay, that's very good. But this, your force per unit area, you're still using macroscopic point of view. Here, you may see, when we talk about temperature, we talk that each particle, small ones, start to move faster, yeah? Averagely, in all directions, it's moved very fast, but they start to move faster, the high energy, high temperature. How about pressure? So what's going on with these particles to get this high pressure on here? What they will do, all these particles? They hit the surface, yeah?
They move closer together.
They will not exactly, but the pressure, man, I will tell you that it's equal to average of the change of momentum of per unit area. So if you look in a microscope, if you look in each of the particle when it's move or like hit the surface and go back, it's changing momentum. So it's each of the small particle transfers momentum to the big surface. And when we look over the area, this is how we define the pressure. Okay, just let me give you now like this example. Okay, average of change of momentum on unit area. That was tricky one. Okay, so you can see that you can relate microscopic to microscopic. Yeah, sometimes it's tricky, but you can. Okay, so now we're done with these ideas. That's a sort of big ideas, just to make you think about microscopic and microscopic, because this we will connect one with each other, and you'll see how they correlate, like how we can describe objects from one point to another one. And sometimes we'll focus more on microscopic, sometimes more in macroscopic, but you should understand that we still describe the same object, and you sometimes as scientists need to learn how to step back and try to figure it out which point of view I want to use to have a better explanation of mechanism of what's going on. Okay. It's difficult. I'm not expecting you master it by the end of this class, but I hope you will have a little bit of better idea. So as you continue, for example, do some research and you will need to do some modeling, you will be able to incorporate, for example, microscopic parameters to explain microscopic behavior, or microscopic parameters to explain bigger macroscopic behavior. I'm not astrophysicist. Do we have here astrophysicists? Any astrophysicists? Yes? with me?
I am an astrophysics major.
Good. So I have some astrophysics. I'm just letting you know I don't know any astrophysics. So if you ask me any question about astrophysics, I will not give you answers. So, but in astrophysics, you do the same thing, yeah. You try to look in a small behavior over on a small scale, and then you make a generalization over the whole universe. Yeah. Try to see the patterns and try to see how the small things end up to contribute in the whole big universe scale. So the similar idea, but in this case, instead of molecules, we're looking like say planets. Okay, so that's for your idea. Now let's talk about second topic. Wow, we go quite slow, so I'll need to speed up. So let's talk about temperature and thermal equilibrium. Temperature and thermal equilibrium. Equilibrium. Okay. And first subsection will be temperature. Okay. Okay. So what is the temperature? It is what you measure with a thermometer. Yeah. What you measure with thermometer. Okay. Okay. So I hope this subject will be quite straightforward, guys. You know it, but we just organize it together. So if we have one object 1, and we have here object 2, object 2, and the temperature of the object 1 is T1, and object 2 have a temperature T2, and if we move them together and they touch each other, what will happen? Guys, I'm sure you should know what will happen if we put two objects together and they will touch each other.
Temperature will transfer from the hotter one to the colder one.
Exactly, until these two objects will reach thermal equilibrium. So we have a relaxation time. Thank you, guys. Relaxation time. And then these two objects, T1 and object 1 and 2, will have the same temperature T, okay, and they both reach thermal equilibrium. Okay. So what if we don't want them to reach thermal equilibrium? Sometimes we need to put thermal insulator, yeah? For example, when we have a hot cup of coffee, we don't want it to get cold very quickly. So we put thermal insulators in our thermal cups, which help us to preserve the temperature. Yeah. So will it fully stop? No, but it will slow down the process of reaching equilibrium. Okay. So it will increase the relaxation time because there is no perfect thermal insulator. Yeah. To prevent thermal equilibrium, need to put thermal insulator. For example, fiberglass. Okay. And as a result, what will happen as a result? We'll have still slowly come to equilibrium. So relaxation time increase. Sorry, I'll use this arrows. Up arrow, it implies increase, okay? I'll start to use some of the notation for you. So relaxation time increase. Okay, relaxation time increase to reach equilibrium. Okay. So I think that's clear. Yeah. Now let's talk about next point. Let's talk about 3 types of equilibrium. Okay. Okay, 3 types of equilibrium. Okay. So we can have, let's here, right here, types of equilibrium, type of equilibrium. And here we'll talk about exchange quantity. Oh, sorry, quantity. I try to move quickly my hand so you can write down, guys. So we talk about 3 types of equilibrium. So we talk about type of equilibrium, here exchange quantity. So the first one is thermal equilibrium. And what is the exchange quantity is energy. We exchange energy, yeah. So we can have 2 different temperature objects, and if they touch each other, they will exchange energy. 2 different temperature objects. Okay. Okay. Next one, it is mechanical equilibrium. Okay. Mechanical. Unbalanced forces. Okay. So what happens if we have a mechanical equilibrium issue? So in this case, we can exchange volume. For example, we can have a balloon. When we have a problem with a mechanical equilibrium, we have an issue with a size, so it could just change its volume, expand it out, have a bigger space, and it can create equilibrium, okay? For example, expand volume. Okay. And final one is diffusive. Okay, chemical. And here, to exchange quantities will be particles. Okay, particles need to come and cross the boundary, so you have the same amount of particle concentration in each area. Particles. Okay, and here example, 2 gases. Okay. So when all 3 types of equilibrium are satisfied, the system is in a state of thermodynamic equilibrium. And in this case, it can be described by macroscopic coordinates. So when, let me put like that, like this. When all 3 types of equilibrium are satisfied, the system is in a state of thermodynamic equilibrium. thermodynamic equilibrium. When all three types of equilibrium are satisfied, the system is in a state of thermodynamic equilibrium. Okay. And in this case, it can be described by microscopic coordinates. Okay, questions? Guys? Everything's good? Great. Guys, if you have any questions, please just turn on the volume, ask a question, okay? So I assume if there is a quietness, everything is good, everything is clear. So what is the temperature in this case? We can go back to temperature. So temperature, we discussed, it's something which we can measure from thermometer, or what we can define as a temperature is the measure of the tendency of the object to spontaneously give up energy to its surroundings. So it's when two objects are in thermal contact, the object that tends to lose energy is at high temperature. It's exactly when what one of you, who was it to mention it? I'm sorry, I don't see your faces. It was someone who said exactly the same words before. So temperature is a measure of a tendency of an object to spontaneously give up energy to its surroundings. Okay. When two objects are in thermal contact, the object that tends to lose energy is at higher temperature. When two objects are in thermal contact, the object that tends to lose energy is at the high temperature. Okay. I mean, today's all subjects are quite straightforward. It's just clarification. Maybe you didn't thought from microscopic and microscopic point of view, but you'll see after a couple, by next week, you'll start to see new information. But here we just try to sort it out, some of the parameters for you, some of the terminology. Now it's another one, the last subsection for today. Let's talk about thermometers and scales, something fun to learn. Number 3, thermometers and scales. Okay. Let's talk about 3.1. We'll talk about temperature scale. Okay. So there is a different types of way how people defined make a thermometer, how we can measure temperature. So before people use 2-point scale to create a thermometer. So before, 2 points scales were used. Okay. So you choose two convenient temperatures. Sorry, let me rotate it like two convenient temperatures. For example, in 2 points of different phase of materials. For example, water when it's frozen and water when it's boiled. We have 2 points, and then we define this will be, let's say, in our case, 0 for Celsius, 100 for when it's boiled. Then we define, oh, let's have here hundreds grade like subscales between them, and this will be our temperatures, and this is how we grade it out. Okay, so so what we do in this case, we choose two convenient temperatures, okay, and then assign arbitrary number of numbers of like break scales on equal intervals. Then assign arbitrary number and break scales. Scale, okay, with equal intervals. And this is exactly what they done. For example, in Celsius, we have it 0 to 100 degrees Celsius. Yeah. So what they did, we defined here will be our 0 Celsius. Here will be our 100 degrees Celsius. This is a freezing point of water. This will be our boiling point of water. And again, guys, we're all smart now. You immediately start to ask me, excuse me, Anna, that's not exactly right. What are you talking about? The freezing water of the salt water or fresh water? How about if we'll change elevation? The temperature will change. Yes, you're right. That's why they specify in the regular ground, in the middle of Europe, with a fresh water. This is what's going on, okay? This is when they define first time. And then in the United States, we use a Fahrenheit. Guys, so you all know that how they define now. So here we have 100 points, yeah, for Celsius. And for Fahrenheit, we defined that is a freezing point of water. Sorry, I did not write very well. Sorry, guys. Water. Freezing point is 32 Fahrenheit. And boiling water temperature is 212 Fahrenheit. And here we have 180 points of separation. Okay. So this is what they've done for Fahrenheit. So guys, who knows how originally Fahrenheit defined the 0? It's a weird position for 0. Does anyone know? So originally, Fahrenheit 0 position was defined as the freezing point of briny mixture, which is made from water, ice, and ammonium chloride. It's type of salt. And he defined it, and later he sort of recognized, oh, this is a freezing point around 32, and boiling water will be around 212. And then and the temperature of the body right now, what is the temperature of the body, normal one? 98, 96? Yeah. And I forgot, 98 is normal one. I'm used to Celsius, so correct me guys. 98 or 96? What is the normal temperature? 98. remember what's the normal
I,
temperature.
I think it's 98. Yeah.
98. Okay. I always confused because when in original Fahrenheit was before they scale it out, it was 96. And now when they scale it properly, when they use a 32 for freezing point and 100 or 212 for Fahrenheit and make it equal intervals, it's become 98. But before it was 96. So now I will make you also confused. If you sell 96, it was an old system of Fahrenheit. Okay, so that was done before. We had 2-point system, yeah. But now they come up with ideal gas scale with only one fixed point. Okay, so then we have then ideal gas scale with one fixed point. Okay, and it was introduced by Kelvin in 1848. Okay, and what he found out that in so what he found out that if you have a measure what is the behavior of the gas at constant pressure, P constant, and you look how its temperature and volume behave, he found out that, oh, it goes like that, yeah, for different gases. But then when he will find where this line intersect, they find out that they intersect at the same point, okay? And the same what he did with a graph when he keep volume constant, and for the same graph he changed pressure as a function of time as well. He finds some of the behavior of these gases, and when you overline them, you find out that they all intersect in the same point, and this point is minus 273 Celsius, yeah. And so for low density gases at constant pressure and volume, it goes to 0 at approximately minus 273. So for low density gases at constant pressure or volume, or in this case pressure, depends which graph you'll go, goes to 0 at roughly minus 273 Celsius. Okay, and then he comes up with concept of absolute zero, which is 0 Kelvin, and 0 Kelvin it's equal to minus 273.15 Celsius. Okay. And it was looked again in 1948, and in 1954 it was the system. I'm almost done, guys, with this section. I just want to finish for you. In 1954, accepted single fixed point system, and they use this as a standard where you only need to know one point to define the temperature dependence, and they define this point as 273.16 Kelvin, and this is only one fixed point, and it's triple point of water. Which is in reality is equal to 0.01 degrees of Celsius. Okay, and that's the way how they define thermometer. So 0, when everything goes to 0, nothing moves. And that's second point, 273.16. It's a triple point, with the point where we can have a all three situation. We can have a gas, water, and the gas, liquid, and solid states of the water. And we'll see these graphs later. The water is quite a weird one. Okay. And I made, yeah. Guys, I don't like to do it. Could I have it 2 more minutes and we'll finish this section, just that will be done. Okay, guys. I'll just quickly talk about 3.2, about thermometers. It's just for your information. And we'll finish it. It will nothing related to homework. This is just for yourself to knowledge. You can have different types of based on expansion of materials or changing its resistance properties. So different types based on expansion material of material or changing its resistance properties or changing its resisting properties. For example, mercury thermometer, where with temperature it expands and you see this column of mercury goes up. The same, the water thermometer, there is several types where it's expansion of material, of liquid with a temperature. In 1927, 1948, they introduced the standard time, how they do it. And there is another one, which you know, like mercury ones, but for any of a special one, for example, if you want to measure from 0 Celsius to 660 degrees of Celsius, or from minus 190 degrees of Celsius to 0 degrees of Celsius, you can use platinum resistant thermometers. Resistance thermometers. Okay. If you want to work with a high temperature, for example, from 660 degrees Celsius to 10,063 degrees of Celsius, they use thermocouple thermometers from platinum. Thermocouple thermometers from platinum. This is the most reliable for experiments where you need to know exactly one. And if you want to measure something which is bigger than 10 in the power 63 degrees of, sorry, 1063 degrees of Celsius, you can use optical methods related to radiations. Related to radiations. Okay, I'm done. So I just want to show you some ideas in case if you will work in experiments and you want to find good, reliable thermometer, not just randomly, but the one which will accurately measure for you for experimental purposes with very high accuracy. This is a type of thermometers for different categories, which will work the most accurately. I'm done with you for the lecture today. I hope you learned something new today, even about something very simple. And next time we'll talk, continue. I'll keep this paper. Guys, how could you follow up this format of writing?
Yeah, I'm good with it.
Okay. Good. Oh, thank you, Accuracy. Yes, yes. And you know, somebody looks like, I hate it, and drop out of the class. No, they will not drop out. They will just hate it and will sit quietly. Guys, let me know if you don't like it. I'm very easygoing. I know I didn't see any of you before. I'm very easygoing with criticism. I prefer you tell me. I will try to adapt, make it better. But from responding from students from last year, they like my classes, but they really miss my in-class way of making notes with all the subsections where you put like 1, 2, 3 and subcategories. And I did not want you to lose this part of lectures. Okay. So, yeah, And you can read this paper fine, yeah, guys? Okay.
Yes.
I'm glad that it works in this case. We'll keep this format. Yeah, have a thumbs up. Good. Guys, you ready to go? The lecture is finished already like 2 minutes ago. You all ready to go if you need it? If you have a question, so you want to chat, I'm here with you for next 10, 15 minutes or longer. At 7 o'clock, I will accidentally lose the connection to the internet. But before that, I could stay and talk with you.
No, I think I'm good. So I'll go ahead and say later, guys. Later, Professor. Thank you.
Bye.
Thank you.
Thank you, guys.
Thank you.
If you have a question, guys, you want to discuss or anything, I saw that one person asked about Zoom recordings. Please keep it here. I will be happy to hear your comments. I'm all about to make your life here as best as possible. You already live in a miserable condition of staying and having online classes. I'm very much sorry for you. So my goal is to make it a little bit better. I couldn't provide you candies because I couldn't ship it to you, you know, but at least I could more or less support you.
Thank you. Thank you. Bye.
Bye.
Thank you, Professor. Bye.
Bye.